enters the other reduced power takeoff, which is much more commonly used and in fact is used across almost all operators, and that is flexible temperature takeoff. A flexible temperature takeoff does not use toggle detent anymore for the takeoff power setting. You're putting the thrust lever when you take off to the flex MCT detent, and it will then use the value you have set in to the MCDU. Let's take a look at the engine thrust curve here to understand the flexible temperature that I keep referring to and how it relates to the performance. If we take it very basic right here, I have a small graph that has thrust on the vertical axis and outside air temperature on the horizontal axis. I could draw a very simple graph like that and show that performance on the engine, thrust, decreases with increase in temperature. And isn't that true? If it's hotter outside, I get less performance out of the engine, as the air that comes into the engine is already heated up, lower density. Lower density means less performance. Conversely, you can look at it the other way and you can say a reduction in outside air temperature gives you more thrust. Does that mean that I can just keep getting more and more and more thrust if it gets cold and cold outside? So that if it's minus 10 degrees outside, my engine is just supercharged and overpowered? Of course not. The manufacturers have built in limits to the engines so that when we have very dense air outside, such as low temperatures, the engines do not overpower themselves. We call that a flat rating. A flat rating is a limit on the engine that if the temperature outside, the density increases above a certain value, the engine is capable of producing the same amount of thrust but with less effort. It means less fuel flow, etc. We call it EGT limit. This right here, as you can see the line flat lines, it is a flat rated limit for the engine, flat rating. If you bring it a little bit closer right here, then we can see that our temperature graph right here produces a value for a temperature that we call Tref. Tref, reference temperature, is the temperature at which, if the temperature is above, then the engine loses performance. For every 1 degree above that temperature, we get less and less and less power out of the engine. But at any temperature below that, any degree below, the engine will not produce more power. It will just be able to produce the same power, but at less effort within the engine. That's not for us to decide. And how does that relate to us when it comes to the actual flexible temperature? Well, if you look at it like this, let's say that our outside air temperature right here, it's very cold. So that produces a maximum power output, which is right here. It can't produce anymore. And that right here gives us maximum power. Maximum power is toggle power. We can't get any higher power setting than that. But we can actually relate that straight into a weight, maximum takeoff weight. Because if that is the maximum power I can get today, then that must be the maximum weight that I can take. I can get more power, therefore I can't take more weight than that. If I were to take this weight, I will need that power, which I can get. So that's very simple. Maximum power equates to maximum takeoff weight. If we are to look at a temperature, let's say it's above Tref, here we have high temperature. The high temperature will only give that much engine power. See, the engine power has reduced. And if you can only get that thrust, but not the maximum thrust, then we can only take off with that maximum takeoff weight. And that's why you had to calculate the maximum takeoff weight before. Because, for example, with outside temperature, you get less and less power. The higher the temperatures, you get less power available, and that equates to less maximum takeoff weight. The graph here becomes very interesting if we look at a scenario. Let's say, for example, today it's 21 degrees outside. 21 degrees outside will give us very good power. It'll give us a flat rating power, maximum power right there, and a maximum takeoff weight of 74.8 tons. Very good. I go out to my aircraft and I load it up. But I found that today we're actually only at 68.2 tons. We're not even close to the maximum takeoff weight. And despite my effort to put more weight on the aircraft, there is no more weight to be given to us. Hence, I'm going to be taking off at that weight. If I need to take off at that weight, do I need that power? No. For that weight, I only need that power. And if I only need that power, I need to tell the engines only give me that power. This is no longer a percentage. This is an exact value for that thrust setting for that weight under these conditions. And on the graph, we could draw a line right there that goes over to the temperature graph and then drops down and says our flexible temperature is 62 degrees. What is 62 degrees? Well, in reality, 62 degrees in terms of performance is the amount of power that the engine will produce as if it was 62 degrees outside, as if it was actually physically 62 degrees outside. Of course it's not, but you don't have that much weight. So you're telling the engine, I only need to produce enough power today as if it was 62 degrees outside. You're giving it a temperature value for the outside conditions, hypothetically, as if it was 62 degrees. And that will allow you to get the performance for 68.2 tons. This graph right here is used only to illustrate to you the concept. I'll be showing you in a minute how we calculate the values. As we have lower and lower takeoff values, we also require less and less takeoff power. But we're not allowed to keep decreasing the power. As you see, there is a regulatory restriction that says no reduced power takeoff may be reduced by more than 25% at any given time. Hence why the derated takeoff was maximum 24 degrees reduction. And it has to do with the turbofan high ratio bypass engines today and their response time to maximum power setting in case you need it. This allows the engine to spool up but comes with a time delay, and the lower the reduced power setting, the longer that takes. Maximum 25% reduction in power, and if we were to translate that 25% for this particular engine into a flexible temperature, it gives us a maximum flexible temperature known as Tflex max. When we calculate the Tflex for today, the value we want to use today, we will make sure that our Tflex is above Tref but below Tflex max, somewhere here. Then we benefit. Having a Tflex value that is higher than Tmax is not allowed, and any value below Tref or actual outside conditions will not be beneficial, as we will simply be flatlining, giving us maximum torque power anyway. So in this scenario right here, it is very simple that for an aircraft that's only 68.2 tons, I don't need full power. I can save all that power and therefore saving the engine life. Give me only that power, and I do that by programming the MCDU and hence the FADEC to a flexible temperature of 62 degrees. There are again limitations and requirements for this type of takeoff. Thrust, for example, must not be reduced by more than 25%, as we just saw. The maximum flex temperature on the engines we use is ISA plus 53, which gives us a maximum rating at sea level of 68 degrees Tflex. Flex cannot be lower than Tref, or the outside air temperature that we just established, because that would be a flat rating, and power will actually be equal to the outside air temperature, so you won't benefit. Flexible temperature takeoff is not permitted on contaminated runways. Derated takeoffs are, but flexible temperature is not. Only toga power or derated takeoffs on contaminated runways. On dry and wet runways, we can use flexible temperature. And we use the Flex MCT detent on the thrust levers when we take off with the flexible temperature takeoff option, and that allows us to still have toga power available. So in case we have a failure and we need it, we can just put the thrust levers forward to toga, and toga power is always available, making this the preferred choice for takeoff. This was a short video on a specific topic. If you want to see the full video or see the hundreds of videos we made available for professional content on aviation theory, head on to our e-learning academy at academy.mindspacex.com. And don't forget to hit the like button and the subscribe button to follow us. We're going to be putting out these videos regularly.